Here's an example of a synthesis problem where we're given a target compound and an array of starting materials where we actually don't need to use all three starting materials. We do need to be, for those three materials to be our sole sources of carbon in the product, but we just don't need to use all three of them. Pause the video here if you'd like to and see what you can do. One thing to note as we look at our starting materials and our product is that we have an aromatic ring in the product which could have only come from bromobenzene. We also have a 3-carbon fragment attached directly to the ring, so we know we need to make a new carbon-carbon bond here between that 3-carbon fragment highlighted in blue and the ring highlighted in green. And we have 2 3-carbon fragments to choose from. So what we could do is imagine a coupling reaction between, let's say, the first two. We definitely have to use bromobenzene. But if we recognize that the carbonyl carbon is a good electrophile, and that means if we make the benzene ring into a nucleophile, we can couple the two together. So let's start there. And first we need to turn the benzene ring into a nucleophile. So let's use magnesium metal to make the Grignard reagent. We can then take our acetone, our ketone starting material, add it followed with a little bit of H3O plus to give us our new carbon-carbon bond. So we have the benzene ring, we have our new bond, and we'll get the product in the form of an alcohol. All we need to do then is convert the alcohol to an alkyl halide. It's an organic 1 reaction. We could use HBr, we could use PBr3. Either one of those would work just fine. Another option, or we can think about how we might use the second 3-carbon fragment. We'll notice we've got 2 halides. We can't couple them together directly, but if we could turn one of them into an organometallic, the other one could potentially be a leaving group. What we want to recognize is that the bromine is aryl, the alkyl halide is secondary, and so neither one of them is suitable as a leaving group unless we use a cuprate. So one option would be to convert our arene first into an organolithium compound using lithium metal and then using copper iodide to create our diphenyl cuprate. And then we could react it with our alkyl bromide. That would give us the structure, carbon framework at least, that we want. The only thing that we'd be missing would be the bromine functional group. And then to figuring out how to make that conversion, we just need to use our new benzylic radical halogenation reaction, where we use NBS and heat light or peroxide to replace that one benzylic hydrogen with a bromine. Now alternately, we could start with the isopropyl bromide, react it with lithium, and then react that with copper iodide to give us lithium diisopropyl cuprate, which we could then react with our bromobenzene. So all we're doing here is to reverse the nucleophile electrophile roles. That will produce the same isopropyl benzene as we did in the first route, and then we can do the NBS reaction again. So either of those two, or the reaction through the alcohol would be a viable synthesis in this case.